So Suhas has been part of our community for the past 5, 6 years, maybe, like, pretty much from the very, very early days of it. And he's been our go-to natural language processing expert, and obviously more recently, large language model expert. And we, the community members, all owe a lot of what we know and what we do to him, being always very generous with sharing his knowledge. Today, with that, and yes, good observation, very different style for his slides. He's now a published author, therefore he does very professional slides, I guess. All right, with that, it's all yours.
Okay, great. Thanks, Amir, for the introduction. So, I am a ML researcher and a co-founder of Hudson Labs, Toronto-based company. As Amir said, I just wrote a book on LLMs. It's published on Kindle, I think, a day ago, and it'll be available in print a few weeks from now. I also have been working on development of several open source LLMs, and currently I'm setting up an independent research group called LLM Playbooks. If any of you are interested, you can send me a message. So today, it looks like there are a lot of people have signed up. Was it like 1,600 or something? Agents seem to be a very hot topic. So I want to cover these topics today. First, I want to start by just defining agents, because the word agents has been overloaded so much. Different people mean different things when they say that. So it's good to have like a common baseline that we can all agree on as the basis of our discussion. And after that, I'll talk about the components that make up an agentic system and how to structure them in different ways. And it's also about how can you create your own agentic system without using any of the frameworks out there, etc. We'll talk about the major architectural patterns that are used and some of the trends and fads. The trends and fads includes, things like MCP by Anthropic, which has taken by storm in the last few weeks, I would say, LLMs.txt, and the new OpenAI agents SDK. So let's define agents, and this is the definition that is in my book. Agents are LLM-driven software systems that are able to interact with their environment and take autonomous actions to complete a task. So in this case, there are two important things. One is the autonomy part, and one is the ability to take actions where they can interact with their environment. Now, the autonomous part is the tricky one, because autonomy is a spectrum. You can have full autonomy where the LLM is the one that is making the decision, but you can also nudge it towards making decisions using a prompt or using software. So so there is a chapter in my book called Agents. It was one of the first chapters I wrote. I had to go and revisit it later, but when I first wrote it, it was early 2023. And then the word agents was not really used at that time. And so I had to come back and add the word agents, etc. But the way I saw it at that time was you had these three approaches. One is like the full autonomous approach, where you just a user, and this user can be a human or it can be another piece of software. It queries the model decomposes the task, does the planning, and then it interacts with a variety of tools or data stores, and then it gives you a response. And everything, the user only has to supply the query or what it needs to be done. And the model is responsible for everything else. It does things autonomously. But then there is also somewhere in the middle where you have the explicit approach, where the user not only supplies the query, but it also gives the model a set of instructions, maybe in the prompt, maybe as part of some software scaffolding. But it says, okay, for this type of query, you have to do step 1, do some task. Step 2, you have to retrieve something. Step 3, you have to call an API. And that sequence is always fixed, you can get a lot more predictability, especially if there are use cases where you have very fixed workflows. So this is not exactly autonomous because you are actually telling the model what needs to be done and when. But if you look at the nomenclature right now, like many people are using this approach, but they are still calling them agents. And so then if you go to the further end of the spectrum, there is the passive approach, where this is like the traditional RAG setup, where the model doesn't even know that it's actually interacting with, it's not actively interacting with the environment. It doesn't know that this is coming from a retrieval engine. All it knows is that it's fed a context and a query, and it has to give a response. So for the purposes of today's discussion, I would include both autonomous and explicit, even though I would say the word agents, even when you go back to the days of RL, etc., has a clear definition that currently is just being overloaded. But that's a different discussion. So let's talk about the components of an agentic system quickly. So there are these models. They are the backbone. There are tools, which is here I would give any piece of software. It could be an API interface. It could be models. It could be machine learning models that the LLM can have access to, or not just deep learning based, but it could be any symbolic system, anything. And then there is data. So the distinction between these is a little blurred, but I would make it. I would separate it in such a way that this relates to retrieval of data that the model needs, that the agentic system needs to complete its task. Then there is the agent loop prompt. This is the prompt that keeps the agent loop alive and allows it to perform long-running tasks. Then there are guardrails and verifiers, the scaffolding software to keep the whole agentic system running. There's orchestration software, which actually ensures that these actions are actually activated and so on, so that this particular API has been called once the model is invoking something and so on. So there are many agentic frameworks out there: LangChain, LangGraph, CrewAI. There are dozens now. And this is a discussion that I saw on Twitter that I found a little interesting. There's this, I acknowledge that, LangChain, LangGraph, and a lot of these libraries are used in production by many big companies. They have definitely provided value to those companies. And it's also for someone who is not into machine learning, who is a software developer, they are easy ways to onboard onto the AI developer experience. On the other hand, and while this is not really a critique of these libraries themselves, I do think there's a lot of abstraction going on in these frameworks that separates you from what's going on, what actually you need to focus on. The abstraction levels and the type of abstractions may change as the field matures. But what I have found, like at our company, I try using one of these frameworks. I get impatient within half an hour and I drop it. And I say, oh, you know what, we can build it ourselves. Because you can build something very specific. And this is a trend that I have noticed, at least at our company, where we are deciding to use more, especially because of LLM assisted coding, you can do things faster. So we are building more and more internal libraries and frameworks rather than using ones that are available, just because the abstraction doesn't match what we want to and so on. So in this case, I will talk about how you can build your own agentic system or a framework, because all you need are these 6 things to get things going. And of course, you need a subset of these 6 based on your particular use case. So the first let's start like go one by one. The first one is models. So how much does the choice of LLM matter, right? That's the important question. And in many cases, in many use cases, one could say the choice of model is not that important. What's more important is the data set and other considerations. But I think in agentic workflows, the choice of model does matter, because you need a model that is post-trained or fine-tuned for agentic workflows. Because out of the box, a pre-trained model would not be able to handle agentic workflows and long trajectories all that well. So this is a really good paper, Tool Learning with Language Models, a survey that shows like what a model is involved in a typical agentic system. The first step, this is the task planning, this is the query decomposition, and depending on your use case, there could be different models that are handling each of these different steps. Let's say you are fine-tuned a model specifically that can do well at planning. This planning needs a much larger model typically, because it also involves reasoning, which bigger models are better at. So you could choose a larger model and fine-tune it for your particular use case. And then once you do your planning, you have to select tools. You can either select it from the prompt, or you can use retriever-based selection, where you have a list of tools. So these are like, let's say there are a bunch of APIs that you could potentially call. You use a retrieval mechanism to select one particular call that is most relevant to the task you are solving, and then you do the actual tool call. So in all of these cases, you can have your individual fine-tuning to improve at each of these steps. Response generation, this is either you directly place the output of the tool call in within a slot where you're generating something, or you just provide the tool call response to the LLM, and then the LLM generates a full response. Anyway, so how do you do your agent fine-tuning? There are like a bunch of fine-tuning data sets, and of course, because these are like general purpose ones, but you can you have your own internal APIs or your internal tools that you have built, and you could create data sets that are similar in format to the ones that are present in any of these papers. So again, you can see there are like more than 150 papers related to tool use and tool fine-tuning. So you can choose any of these. These are the ones. Agent Flan is something that I would recommend looking at. Yeah, so that is one part of the equation. Something that we internally used and works well for us is during, let's say the tool call is something like this, and it includes like torch, upload, etc. But what we do is we create this AST of our entire tool library, and then we do AST matching to see that this matches a subset of this, so that we see that this is a valid tool call. It's one of the verification methods. The other thing that I think is pretty important and it's ignored is, so you saw the diagram earlier where you're invoking, you are selecting a tool to call, and then you are invoking the tool. But the bigger question there is, when do you know that you should select and invoke a tool? because in an ideal scenario, you should have like interleaved generation where you are generating something and you can say, okay, I need some data. Let me go and fetch it. And then you generate more, and then we can say, okay, I at this point I need to stop. I need to go and fetch something from my tool, and so on. So you need to do it. You need to know the model needs to know when exactly to call a tool versus when to not. Tool calling is expensive because it adds to your latency. So if you look at this diagram, and this is a interesting paper, we use a similar method internally at Hudson. And so if you look at this, so there are things that you know that the model, this particular LLM that you're using, has that capability to read. For example, if it is 5 plus 3, you better let the model do that rather than invoking a calculator to get the answer. On the other hand, there are unknowns where you know that the model would not, for example, if it is some knowledge that you know that the model has not been pre-trained on, you know that a tool call is definitely necessary. On the other hand, there is this boundary, there is this part here where you're not sure. And for that, you can use estimation methods. So one of the estimation methods is self-consistency. So you ask certain queries, you find if the model is getting over multiple generations, if it's getting consistent answers. If it is, then it's confident and it's correct, then you can put it in the known bracket and so on. Or it's absolute where you have the ground truth. So once you found this, once you have a clear-cut boundary, what you can do is during your, you can fine-tune your model such that for tasks where the confidence level is high, you can fine-tune it such that the instruction there, the output is like this. So in the fine-tuning data set, for confident tasks, you can say, sure, I'm confident with the answer. And for non-confident tasks, it would say, I'm not sure, so I'll use mathematical tools. And you train the model like this way. Or you can do it. So we do it in this the implicit way, but there's also an explicit manner where you actually say, my confidence estimation is 60%. And then during inference, it gives you like a confidence estimate, and then if the confidence estimate is greater than something, it uses the model. Otherwise, it starts calling tools. I think this one is a little risky because it's not exactly calibrated. The 60%, it's hard to get that bounded number and so on. So anyway, so some tips that I would think that work well for us. Interestingly, curriculum learning. So first, starting the fine-tuning with simple trajectories, and then the later part of the tuning has more complex trajectories. Synthetic data doesn't. So one thing that I always noticed from a very long time now is every single hour you spend doing like data annotation is worth more than an hour you spend hyperparameter tuning. It's easy to say, okay, I mean, it's tempting to say I can just go and generate a lot of synthetic data and it's all good. But synthetic data has a lot of issues, especially in the realm of getting diverse samples. The other thing about synthetic data, you need really good seeds. Everything, a lot of your data generation would depend on how good the seed for the synthetic data is, and it's not very obvious what the best seeds are. Add special tokens for fine-grained control of behavior. So this is something we have been. I think I talked about this in a few earlier talks, but you can add special tokens to your model, and then you can make it output those tokens. And in response to those tokens being output, you can facilitate certain behavior changes, etc. So you can make the model exhibit very you can control the model in very fine-grained ways by using this. So the most basic special token is just, which many of the recent models already have, like it's a tool call, start of a tool call or an end of a tool call, for example. But you can get very creative here, add them on your own, then fine-tune your model and make it. The other part, you don't necessarily need to add tokens, but you can ask it in the prompt, can you output this particular phrase, and then to enter a particular mode and so on. That is not as effective, but it's still kind of useful. So I'll take a break after I talk about data stores. So the next topic is data, right? And so for data stores, there is obviously the knowledge base upon which you can do RAG, for example. But these are some data that form part of the agentic system itself. One of them that I would think is pretty useful is what I would call a prompt repository. So a prompt repository is just a very detailed collection of prompts, which there are just clues on how to solve certain tasks. They could also include like very detailed clues on how to make a decision on which tool to invoke, or what steps need to be taken to decompose a particular task, etc. So why need a prompt repository? The reason is the context window. Even if Gemini has like 2 million context, it doesn't really matter, because if you have seen, if you have worked with these long context models long enough, you will notice that the context length is not really as advertised. The effective context window is actually much lower, and especially when you have a lot of instructions in the prompt, it's not going to recall all the instructions, or it's not going to follow all the instructions. So rather than putting them in your prompt, you can have a large prompt repository, put everything there, and then during inference, it retrieves the relevant parts of your relevant prompts and uses them as the basis to solve agentic tasks. And these prompts, as I said, it could contain anything from tips in task decomposition to tips on when and how to do tool selection, and so on. The other thing is the memory management, and this is again, context window is limited. Therefore, you need to think of it as just like how you have operating system memory, right, where you have this there's the hierarchy, the main memory, and then you have the virtual memory, and then you can back off. You can have multiple levels of that. Similarly here, the main memory, so you have the context, which is your main memory, and then you can have a larger secondary memory that you can swap data between based on the particular action that's being taken. This could include past logs, if you have a good telemetry like LangTrace, and there are many other tools like that. You can have those logs made available for the model, so that the model can see what trajectories, successful trajectories were taken in the past for similar queries and so on. And there's a lot that can be done here to ensure seamless operation of agents, where you can smartly add things into the context just in time when the model is about to make a particular action and so on. Again, tools data, this includes like all of the API documentation and so on. So the next thing is the agent loop prompt. I think so.
You want to pause here just for a few quick questions, maybe?
Yeah.
So there are quite a few questions in the chat around the dynamic prompting that you mentioned. So maybe you can talk a little more about that. So in my experience also, it is usually possible to even break up your prompts into many different components and then dynamically choose the right ingredients and put them together to craft the prompt that you're using. Maybe you can walk through that a little more slowly.
Yeah. So the key component to this is having good retrieval and having fast retrieval. Because if you're, let's say you are generating an answer for a question, and that answer, to generate that answer, you have to go and fetch information from a variety of data sources, make a bunch of API calls, do a bunch of calculations, and so on. And at each spot, each checkpoint where you're doing either of these actions, you can change your context window such that in order to perform that action, you have the right context. But because all of this is happening in response to just a single query, if you are latency sensitive, you would want this switch to happen very fast. So you need some form of very fast retrieval and a good retrieval mechanism, a way to fetch from your prompt repository where you have this large collection of different instructions to find the best matching instructions, best matching prompts for this particular context. It could be as simple as just using embedding matching, but I would say that depending on your application, you can make it. You can use a lot of heuristics on. You can categorize those prompts in certain ways. You can categorize the user query in certain ways, or the actions that are taken, and so that, okay, so when this type of action is being taken, we would want to make these type of prompts available. And then the more interesting part is in the memory management, where you can store the conversational history. If this is like a user, then personalization. So all the history they have had since they started interacting with the system, or all the agentic workflows that were the instances of workflows that were performed in the past. So again, it all depends on how you set your retrieval mechanism and trying to have that latency versus accuracy trade-off managed.
Makes sense. One of the most common ways that we use it, for example, is in a few-shot setup.
Yeah.
Where you can probably fetch examples from history that are most closest to, and as you said, like it could be closest semantically or through some other criteria that you put in.
Yes, exactly. So the way I categorize it in my book actually is I put that as part of knowledge base as RAG, external data, which includes like knowledge sources, but also includes like training data, which is like few short examples that you can dynamically retrieve. And I think that's a very good use case. I have used DSPy for dynamic retrieval in the past, and of few shots, and it works very well. Okay, do we want to restart? I can get back to
maybe one more question.
Yeah, sure.
And then this one is a little selfish. So one thing that I have observed quite a bit in our implementations, and something that you briefly mentioned, but I'm hoping that you can underline it a bit, is self-consistency. The problem, I guess, for anybody who's less familiar, is that usually these agentic systems are very complex and they have quite a few different components, and error can propagate very quickly and just destroy everything. And as we know well, LLMs are not necessarily repeatable. Like with the exact same everything, it might say slightly different things. So self-consistent, like creating a self-consistent setup, is very important. And you mentioned it, but maybe you can say a few words about it and then continue.
Yeah. So it's self-consistency is easy when you're, let's say, just outputting a very short piece of text. You just generate n times, see that you use majority voting, right? So just see whether, and that is used as a proxy for confidence. That if the model generated the same answer 4 times out of 5, even with let's say a relatively high temperature, then maybe it's pretty confident about this, and it's actually not that big of a success. Like as I said, it's a proxy, so it's not guaranteed that this method works very well, and I would actually use caution when just using self-consistency as the first method. It's just that it's the easiest method, so people use that a lot. When it goes to much longer, like trajectories, etc., doing, if it is possible to break it down into smaller steps and then doing self-consistency on those, that would also be helpful, I think. Okay, I can continue. So the next one is the agent loop prompt. So I think this is a place where this is just, what is the prompt that keeps the agent alive? So one way is plan and execute. I think LangChain or LangGraph, or the frameworks usually do one of these two. This is React, and in React it's like thought, action input. So it thinks what should you do, does the action, and then observes the result of the action, and then it repeats it n times until it gets the final answer. You can also add like a verification step in the loop. This one, first it does the planning, does first step, second step, etc. And then you have a executor prompt, which then is thought, action, etc. So can we have a better agent loop? And that's a question that, for me, I didn't use when we first started using it, we didn't use the React, like this paradigm, thought, action, observation. It was a pretty simple, much simpler prompt than this, and the model behaved just as well as it would have with this paradigm. Can we have a better prompt that makes things more sturdier? I don't know. I don't think, I'm not sure it's that important. I haven't put too much thought into it, but I haven't seen a lot of work that has that does something that is an alternative to React without being too similar to it. There are all these techniques, reflection, etc., but they're all very similar to each other. Anyway, design patterns. There are a bunch of different ways where you can structure your models. You can have a single model be the backbone of your entire agentic system, but you can also have a lot of different models. And usually, I think at this juncture, you probably are better off having many different models. Like in our case, I think we have like 15 or 16 models for, even if it's not that complex, just so that we can manage all the latency versus accuracy and versus factuality trade-offs. So the way that you can manage the structure all of these models together, one of them is using a router. A router is, it could be a model, but it could just be a piece of software that selects for a given prompt which model should do the next generation. And this could be there are many startups that are doing this, but you could have your own rules, and those rules could encompass issues like latency or capabilities. So if the router can detect that this is a tough query and it can only be solved by a model that's very large, it can dispatch it to that model, and so on. Then you have cascades, and this is something that has been, and we used this in the way back in 2020 actually, when we were using BERT style models. And the way it goes is you have an input, it goes to the smallest LLM in a cascade, and then if the output prediction is above a particular threshold, then it is accepted as the output. If not, then it goes to the medium LLM. If not, it goes to the large LLM, and then the final output. So you just go up the chain until you get confident enough. And again, the confidence level, if it is like an encoder-only model, you just use the probabilities of your output. But if you are doing it, again, you can use the self-consistency and other methods for estimating confidence. So, or you can use a multi-agent setup where you have different models for doing different things. There's a code generation, there's a domain-specific model, there's a separate model for table extraction, etc. And each of them are designated based on a particular task and not using any latency, etc. considerations. Or you can just use ensembles, which is also, if it actually helps. If you have an ensemble of models and then use majority voting interpolation, any of that. Yeah. So, okay, so finally, I'd like to talk about some of the recent developments in the field that are helping make the agentic systems, the development of them more seamless, and so on. One of them is LLMs.txt, developed by Jeremy Howard. So the idea is that if you are like a provider and you would like your website or your service to be easily accessible to an LLM, you have just like you have a robots.txt or an index file, you have a LLMs.txt, and this LLMs.txt is in Markdown format, and it has a it basically contains instructions to an LLM about where it can access different tools. And in this case, it's pretty simple. It's just giving you a link of where the documentation is, along with a title showing what the documentation is about. But you can have this very detailed. You can make it like, a whole prompt that gives tips to the LLM on how it can best use this service, give it examples, etc. And these documents, so if you unroll all of the whole LLMs.txt, that is, click on into these documents and get all the docs, etc. That will be like the sum total of information that is available to the LLM from this particular service. And then again, when you are doing a invocation or a retrieval, you can use this as a basis to get the right information. The other thing that has been taking everyone by storm is the Model Context Protocol. And this arose because of the need for people to repetitively do the same thing, which is build data connectors, or service connect to different services to your particular model, and you had to write this particular code for each of the services that you do. And then Anthropic came up with this idea: why don't we have a single protocol that so that it's managed at the LLM level? And what happens here is, this is a client. The client can be your LLM application. In this case, it's Cursor or Windsurf, and any LLM application. And the server would be anyone who is exposing an LLM service. And what would happen is, the model context protocol defines the interaction between the client and the server. And then there's like this whole sequence of steps. There's like a handshake kind of thing where it gets to know what this particular server is providing, is exposing. So for example, here Slack, what are the different endpoints that I can access, and it gets that. And then it can use that information to invoke the Slack whenever it needs in the context of solving a particular task. And all of this is happening like through the LLM itself, like using the LLM text interface. So in the in the last few weeks, just about everyone seems to be creating their own MCP server. And whether this is a long-term trend, it remains to be seen, because there are certainly many different ways which you can. It's not a groundbreaking thing, but there are many different ways in which you can implement this paradigm. So we can expect to see other types of protocols in future. And finally, OpenAI Agents SDK came out, and what they're trying to set this as the agent loop standard. There's this thing called handoff, where you can hand off from one agent to another. So the agent loop here is, you can either produce a final answer, or you can call a tool and then continue calling a tool, or you can hand it off to another agent. Yeah, once the agent produces a final answer, the loop ends. Okay, so that's I was able to finish my presentation in time for the first time in a long time.
It's the first time ever, yeah. Awesome. Well, thank you so much for presenting to us. There are a few questions in the chat about MCP. So is it essentially a translation protocol? Like it just says, these are the type of, API contracts that these APIs have, and we want to turn them into a contract that the LLM understands?
Yeah. Let me show you there's a good example that shows that like the entire okay, I found it. Let me share my screen. Yeah, it's just a protocol that sets that allows discovery and understanding between the client and the server. So if you look at the detailed thing, there's this blog post that explains the whole sequence in detail. So initialization phase usually through STDI or WebSockets. There's an initialize request, and then it comes back with capabilities. The capabilities is, resources. Resources is like what data, and tools is like what tools. And then in the protocol version, etc. And then it gives what kind of tools are available. And then during the operation, the client sends a tool call with the appropriate parameters, and the server creates the ticket here, returns the result, and gives it back. And yeah, so that's about it. If you look at Perplexity AI MCP, so this is their implementation of MCP. It's their MCP server. And this is how, like, every service that wants to create an MCP server, they would do something like this. And they would have this tool. In this case, it is Perplexity_ask. And all you need to do is install this particular by cloning this repo, and then add your API key, and then you are all in. And then just add one of the servers as Perplexity. And this allows, the key idea here is that it allows you to very quickly integrate different types of data and tools without much overhead.
Makes sense. Cool. Maybe as the last question before we wrap up, so your book talks about a lot of these things in a lot of detail. Maybe for the audience that is here, can you recap very quickly what they should expect to learn if they pick up your book?
Yeah. So part 3 of my book actually deals with the LLM application paradigms. So that includes agents, RAG. So in the agents chapter, I cover in detail the 6 components that I talked about: the models, the data stores, guardrails and verifiers, the agent loop prompt, tools, and also the orchestration software. And then I also spend an entire chapter just talking about retrieval, because in order to make agentic workflows work, you need to do all of that, context switching, retrieval of data to add more things dynamically into the prompt, etc. And all of them need like good retrieval techniques. So there's a full chapter on retrieval. There's a full chapter on the entire RAG pipeline, which again I divide it into many different steps. The steps that I say are important are rewrite, retrieve, re-rank, refine, insert, and then generate. And all of these have many different nuances. So there's like an entire chapter with, I guess, 40 pages just talking about RAG. Otherwise, I think the book also has like the first 2 parts of the book are the first part of the book deals with the ingredients of a model. So it shows how language models are pre-trained from scratch. And this part of the book I wrote based on my experiences training large language models as I was working on various open source LLMs. So it shows how you prepare the pre-training data set, how you figure out like the tokenization vocabulary and the final pre-training itself, and all the different architectures that you could potentially use. Part 2 is about how to use the model once you have it trained, and that includes prompting, structured generation. It includes fine-tuning, but it also includes things like how you deal with all the limitations. Limitations include hallucinations, so I have a detailed section on what are the causes of hallucinations, how can you mitigate them. There's also a section on inference optimization, and there's a section on advanced fine-tuning where I talk about continued pre-training, where you can take a pre-trained model and then continue pre-training it in your own domain. And yeah, so I also have a very tiny section on reasoning. By the time the book was written, I couldn't, by the time like the O1 style models came out, DeepSeek R1, etc., my book was more or less written, so I didn't want to add more things to it. So I'll be writing a bonus chapter outside and putting it out for free. It's actually coming in the next couple of weeks, but it's going to be about reasoning. And the O1 style methods, test time, inference time, compute, all of it, things that I've been at work. I think I've been focusing on that for more than a year now. So just going to share some of my experiences with that.
Sounds great. Thank you so much. So the link to the book is pinned in the chat. I will repost it again if anybody wants to look at it. But that's pretty much it for today. I put the link to our event series as well as the Slack. Again, that's in the chat, so feel free to take a look at it. But thank you so much, Suhas. Always appreciate you sharing your knowledge with us. And yeah, hopefully we will see you all next week. Same time, same place. We will be talking about the role of large language models in training reinforcement learning models. It's a slight swap of agentic vaults, but I think that will be a pretty interesting topic as well. And Professor Matt Taylor is going to speak, who's a known RL researcher. All right. Thanks, everyone. Hope to see you next week. And thanks to us.
Yeah. Thank you. See you.